Hey everyone, I don't know if you all can hear me yet. I know some of you are still joining on audio. We're probably going to have a few other people coming in over the next few minutes. Probably we'll wait till like 5 minutes after 3:30 to get started here. But yeah, it looks like we're going to have a relatively small group today too, which I kind of appreciate given that we haven't done this before. Uh, so I think the goal with this is going to be to have you all, depending on how many people we get, have you all ask questions just as needed throughout. If you don't want to interrupt me with a question, you're welcome to type it in the chat. Sam here, I don't know if you can all see the same gallery view that I can see of everyone, but Sam is one of our newer tutors we just hired not too long ago. He got a really good score on the MCAT. And so he's going to help answer questions in the chat as well as kind of have be involved in this conversation as well. Given the small number of people, I think we can be relatively laid back about this though. I also appreciate any like feedback that any of you have for this because this is something that I'm wanting to get going. And I used to do at a high level with Kaplan whenever I taught their live online course, but I haven't done it in like 3 years. And I'm just trying to think about the best ways to go about all of this. So might give people just a few more minutes to join. Just as a general overview here, though, what I'm planning on talking about is organic chemistry because that was the slight majority of you chose that in your survey. I've been thinking for the last hour or so about how to cover all of OChem in an hour or an hour and a half, and obviously that's not really possible. But I think that I can give you some better ways of thinking about how reactions occur, whether a reaction is going to occur or not, what is the idea of stability, why certain intermolecular forces are favorable over others, generally how solubility works as well as part of this. And so that's just like a general overview of what we're going to talk about here. Does anybody have, and I'm just going to open it up to you all right now. I know that it might be chaos if you try to all talk at once, which is part of the experiment we're doing here. But does anybody have any like one topic in particular in OChem that they're really hoping to get covered today outside of that broad scope that I was just mentioning? You're welcome to say it or just type it in the chat. I don't care. Whatever works for you.
Okay, if you don't mind
Yeah,
me
go ahead.
stepping in for a second.
Yeah,
So, aside from like going over like OChem in general,
yeah,
can we cover like what the MCAT tends to like really focus on in terms of
yeah,
OChem and like what aspect they expect you to be able to apply and think about?
yeah,
Because
definitely.
like
That's
MCAT is like such a broad, like OChem is such a broad spectrum. So like my question is like what do they really focus on and what do they test on in particular?
Yeah, absolutely. We're definitely going to talk about that. And then near the end of this, also what I'm going to ramble for a while here, I think. But near the end of it, I'm going to once I shut up at the end, we're going to open it up for questions from any of you and kind of take the discussion in that direction as well. And Sam is also going to say some about kind of how he prepared for OChem on the MCAT too, because
Okay.
he studied. You studied completely independently for the MCAT, right, Sam?
Mm-hmm.
Okay, cool. Yeah, so he's gonna just talk about processes that he went through whenever he was studying, just to help drill some of this in or help gain a better understanding of that. And I can talk about some of that too. Um, so I think we're probably good to get started though. It's 5 minutes after. Uh, I'm not sure exactly how long each part of this is going to be. I do have a meeting that I have to be at in 2 hours, so the whole thing will be 2 hours max. I'm just letting you all know. Don't feel obligated to stick around though if you feel like we're wasting your time. Um, Also, there's a chance that I might go a little too fast in this for some of you, or a little bit too slowly for others of you. One thing that I'm considering doing is getting the video of this meeting later and then getting feedback from all of you on things that you could benefit from, where you could benefit from further elaboration, and then make like short videos addressing those different points that would link off of the primary discussion. Let's see. Okay, cool. Yeah, see, I got your message, Samir. Yeah, we can definitely look at that. I might need to review those, to be honest. I don't know if he sent that to just me or to all of you, but one of the students just asked if we could do Strecker and Gabriel synthesis. Those mechanisms tend to be the type of thing that show up in passages. on this test. And so the hyper specific mechanisms like that uh, are really good to know if you're trying to get every single point on this test, which, theoretically should be trying to get every single point, but it is kind of off the beaten path of what's most likely to show up on the test, if that makes sense. But we can definitely talk about it. Yeah, so we'll do that for sure. Probably near the end though, I would say, because that's like a really hyper specific thing. Okay, I'm gonna go ahead and get started here. And also, please, like I said, please feel free to type messages in the chat. Sam, if multiple people like ask the same question, or if it seems like a lot of people are wondering the same thing, please interrupt me, and then we'll just dive deeper into whatever that same thing is, because I want to make this as useful for all of you as I possibly can. I'm going to just go ahead and start by sharing my screen because that's what I'm going to be doing most of this whole time. I've got a couple things written out here, a few things prepared. There is also a OChem passage in one of the AAMC full-length exams that I would have loved to go through for this. I've got it pasted right here. I'm not going to show it to you, I promise. No spoilers. I decided it's not a good idea to go through it because most of you probably haven't taken AAMC number 4 yet, or are hoping you have forgotten everything from AAMC number 4 so you can take it as a simulated MCAT before your real test date. So I took a few things from that passage and modified them significantly so they'd be unrecognizable, and we'll just talk about those kinds of reactions. But the purpose there will be to go through how to think about reactions you've never seen before, because that's going to come up all the time on this test. And the general idea is the same as throughout the MCAT, where you take the simple basic science ideas that you are familiar with, SN1, SN2, other nucleophilic substitutions, that sort of thing, and then apply it to a much more difficult concept. So that is just the general approach. You're going to see you're going to hear me say that a lot if we talk more and more about OChem, because that's really how OChem works on the MCAT. So just to get started here, when I was thinking about what exactly we wanted to talk about today, I was really trying to think, what are the most relevant organic chemistry topics on the MCAT? It's really hard for me personally to differentiate organic chemistry from biochem on one side and gen chem on the other side, because in reality, they all are sort of the same subject. But when I was thinking about the crux of OChem on the MCAT, I really came down to two different categories of things. One of which you can see here, I've got intermolecular forces written. The other is reactions in general. And obviously, there are a lot of reactions you can need to know to do well on this test. Tons of different types of reactions can show up. However, you'll find that there are some general principles that govern all of chemistry that you can lean on if you do forget the reaction, or if you need to figure out what the reaction are. So that's one of the things we're going to talk about. And we're also going to talk about intermolecular forces and how they govern so much of biology and biochemistry, and how you can use this concept of intermolecular forces to determine whether a given reaction is even likely to take place as well. So jumping off into that, first and foremost.
Hey, Joe,
yeah.
Sorry, I'm gonna interrupt you.
Yeah,
I don't know if you're intending to share just the Kaplan books that you have there.
No, that's not what I intended to share. I appreciate that though.
Yeah.
Yeah, thanks. I will share the other screen. Now I've got some resources up right now to reference if I need to. Let's see here. Yeah, thank you so much for the update though, because I was in another meeting earlier where I was sharing the other monitor. Can you see the OneNote thing now? This is good. Like, what is stability on it? Okay, cool.
Yeah.
All right. So starting from starting out with that question in general, we'll move the forces thing over for a second. The idea of stability is something that like everybody who studied chemistry at any level has heard. Like, this compound is stable, or this compound's not stable, and therefore it either reacts or it does not react. But I just wanted to briefly discuss what that idea of stability actually means. And so to look at that, and you'll see this is equilibrium kinetics. We won't necessarily talk about that here, but this graph where you have delta G on the y-axis and reaction coordinate on the x, and you're looking at products and reactants and activation energies, all of that is really the crux of what stability is. So stability is just how likely that compound is to exist in the future. If it's more stable, it's more likely to exist in the future. So its presence on this G axis is obviously going to be lower. This is determined by things like ring strain, if there is a ring. It's also determined by things like steric hindrance or localization of charge versus distribution of charge across a molecule. The charge thing is one that we're going to talk about a ton. here, it also has a lot to do with the context in which that molecule is found. What I mean by that is the solvent for the reaction. So for instance, if you've got something that is charged, that thing that is charged is likely to stay charged or to remain charged in a more likely to positive charge. We'll talk about that in a second too, if it's in water than if it is in an organic solvent, just for instance. Similarly, a charged product is more likely to form from a reaction if your solvent is water versus an organic solvent as well, because water or other hydrogen bonding solvents are likely to stabilize that charge. So starting out with the intermolecular, and that's where the intermolecular reactions or intermolecular interactions come in here. So, and we're looking at things on this axis and thinking about whether a reaction, that's how we want to think about whether a reaction is or is not going to occur. One of the topics that you'll see referenced over and over again on the MCAT is just presence or absence of hydrogen bonding capacity, or presence or absence of hydrophobic interactions. So, and I keep wanting to also throughout this, I keep wanting to ask, does anybody know this, or are you familiar with this? Because I'm so used to doing these one-on-one meetings. So I'm having to choke that down as I'm going through this. Although I may just start doing that because there are a relatively small number of you in here. But there is a rule that I've given some students who have worked with me in the past that I made up whenever I first was studying for the MCAT, that I think can be useful for looking at this idea of hydrogen bonding and whether or not something is going to be super stable in a solvent or not. And so I'm just going to go ahead and show you that right now, simply because it's super useful. So over and over again on the MCAT, you'll need to determine whether or not a molecule is likely to be stable in water, or whether it's soluble in water. And so the way to determine that is to look at this idea of hydrogen bond opportunities. And so what a hydrogen bond opportunity is, I'm just going to write a hydrogen bond op. Hydrogen bond opportunity equals number of, it's a heteroatom attached to hydrogen. So meaning like nitrogen, oxygen, fluorine, more or less attached to hydrogen via covalent bonding. So if you want to determine whether a molecule is likely to be soluble in water, you just want to count up the number of hydrogen bond opportunities on that molecule. So like, for instance, if we were to look at water, number of hydrogen bond opportunities here equals 1, because we have that one oxygen that is attached to 2 hydrogens. If we wanted to look at like ethanol, right, CH3, CH2OH, number of hydrogen bond opportunities there is also 1. If we wanted to look at something like phenol, right, again, 1 hydrogen bond opportunity there. If we wanted to look at something like acetone, this has 0 hydrogen bond opportunities. Okay, so I think you probably get the point. So if we're trying to determine whether a molecule is stable or not in water, we can just look at number of hydrogen bond opportunities and use that and divide the number of carbons in the molecule by that number of hydrogen bond opportunities to get some number. So like, for instance, if we wanted to say benzoic acid, for instance, how many hydrogen bond opportunities are in benzoic acid? I'm just going to ask you guys questions. So does anybody want to tell me how many hydrogen bond opportunities are in benzoic acid?
Is it 1?
Yeah, thank you. yeah, one hydrogen bond opportunity in benzoic acid. So if we take number of carbons divided by number of hydrogen bond opportunities, what is our answer here for benzoic acid? Well, I mean, I'm not going to keep asking you guys irrelevant questions. I know you can divide 7 by 1. So this comes out to be 7 divided by 1. And so obviously that's 7. And so the rule here that you want to use, this is kind of the punchline of the whole thing. The rule here is that if this number is greater than 5, then the molecule is not soluble in water, is not going to be able to dissolve in water. If greater than 5, not soluble in water. If less than or equal to 5, then it is soluble. And that's the whole thing. So and this is just super useful in my opinion, because it's a hard and fast rule that you can just use to determine whether or not something's soluble. So many people might say that benzoic acid that I just drew there is soluble, but if you use this rule, you can very quickly determine that it's not soluble at all in water. And this becomes really, really useful whenever you're trying to determine what solvent something might show up in whenever you're looking at questions. So for instance, let's say we did a reaction where we have like benzene and we just add that carboxylic acid to it. Okay, I'm not going to draw the whole thing out, but if you do that reaction, what you're going to end up with is a solution where you have benzoic acid dissolved in benzene, right? And you might have some electrophiles left in the substance that you used for that electrophilic aromatic substitution. So in order to get those out, you would dump water in, right? And then all of those go into the water. But if you're not sure about the solubility of benzoic acid, then you could put benzoic acid into that water as well, and then you miss the question, right? How, in whatever way they're asking you about it. But if you just use this rule, then you can know that benzoic acid is going to stay in with the benzene. And then you need to, but then you might still need to think about how to separate that benzoic acid from benzene, right? So in order to do that, there is a way to pull bigger molecules with less hydrogen bond capacity into water. And that is just to make them charged, which I'm sure many of you had already guessed to this point. So all you would need to do to get benzoic acid into that aqueous solution away from benzene would be just to react it with a base, right? If we had something like, this molecule, for instance, number of hydrogen bond capacity on this is again just one, even though there's two hydrogens attached to that nitrogen. Though keep in mind we're tracking heteroatoms attached to hydrogen, not hydrogens attached to heteroatoms. So the number here is just one again. And so if we look at the ratio, right, from our equation that we made over here, then it becomes 7, right? So that means that it's not soluble again. So if we had this and benzoic acid in solution, they would be in solution with benzene, right? Or in an organic solvent of some sort. In order to get one of them out, we need to think about how to make that one thing charged. So if we were to put HCl in, then we pull the nitrogen containing compound out, right? Because we protonate it and make it positive. But if we put a base in, then we pull the carboxylic acid containing component or whatever molecule out because we make it charged, and so therefore it just goes into water. So understanding when things are likely to be soluble in water versus organic solvent is just an important concept here. We can also think about, whenever you're thinking about the ways that reactions occur, it's really important to be aware of the context of the solvent as well. Because, for instance, we were just talking about how charged stuff is soluble in water. Charged particles or charged molecules are relatively stable in water compared to what they would be in a different solution, right? In an organic solvent or in a nonpolar solvent or something like that. But that doesn't mean that they're just stable always, right? Like you see organic chemistry reactions all the time where a negative charge gets put up onto oxygen, right? Or a carbon atom becomes positively charged or something like that. And that compound then very quickly goes on and reacts with something else, right? So if you're looking at that reaction happening, then it kind of becomes clear to you at that point that that molecule is not necessarily stable itself. Otherwise, it would just stick around. Like SN1 would never happen if a carbocation was just inherently stable, right? So even though it's in water, whenever we're doing the SN1 reactions, even though that is happening in water, it doesn't mean that that positive charge just gets to stay there forever. And the reason for that is that the positive charge being localized on a singular atom is just not an entropically favorable situation. We would rather take electrons from something else that has too much electron density and collapse both of those respective charges into a bond so that you have equal sharing of electrons, because at that point you've distributed the electrons across multiple atoms, which is just generally a more favorable thing. At the same time, though, you have other atoms or other molecules that are totally chill, being stable in solution. Things like chloride, right? Chloride's really happy being stable or being charged alone in solution. Same with everything on the left side of the periodic table, right? But not fluorine, right? Not oxygen. Those don't want to be charged in solution. So I want to think about why that's the case for a little bit. Like, why does sodium get to be charged in solution alone, but oxygen doesn't, or fluorine doesn't? Sodium and fluorine are very, very similar, right? Like sodium just has that one positive charge. Fluorine would have that one negative charge, but it doesn't get to be stable, even though chlorine does. So why? Because this is like super frustrating for a lot of people. The reason for this is because when we're talking about not having negative charge, the solution is that we're able to distribute those electrons that were consolidated on the singular atom into a bond between two different atoms. And so that electron density goes from being consolidated around one nucleus to now spread out between two. And it solves the charge issue for both atoms as well. But So that gets you to this idea of spreading out electron density. And if you think about the atoms that are allowed to be negatively charged in solution, we'll go to those first. Chlorine, bromine, iodine, for the most part, those are large atoms, right? Those, they can distribute that negative charge around a very large valence shell. And so it's not so much consolidated in one spot like it would be, for instance, in fluorine. But that doesn't answer the question of why sodium gets to be charged, right? Because sodium is charged just like fluorine is, and it actually is smaller, right? I think, no, it's not. I need to look at a periodic table. Regardless, the reason that the left side of the periodic table gets to be charged and the right side doesn't is because when the right side is, and when I say right side, I mean like fluorine, oxygen, that kind of stuff. When those become charged, they can very easily just grab a proton up out of solution, right? And so then they've collapsed their charge and they formed this bond, and now the proton isn't charged either, right? So we have, I'm going to draw some of this out rather than just rambling so that you guys actually have some visual aids. If we think about like, I want to compare like sodium, which we know is really stable in solution, versus chloride, which we also know is stable in solution, versus hydroxide, which we can be pretty sure is not stable in solution. We can talk about how we know that in a little bit, but it comes down to the idea that it's a strong base, right? It would much rather just pick up a proton and become water. And then the proton no longer has to be charged either. And so these two things just become water together, whereas everything else I've drawn here doesn't do that. The reason that this happens is because once this water molecule has formed, we have, like I said, 500 times collapsed the charge, right? So we no longer have this concentration of charge, which is a good thing for us stability wise or entropically speaking. But we also haven't lost our charged interaction that the molecule is having with the solvent being obviously water in this case, right? So whenever you think about hydrogen bonds, these contribute a lot more to pulling something into solution than any other interactions, like dipole-dipole interactions, for instance. Like if you have two molecules of, or let's say we have a molecule of acetone interacting with the molecule of water, right? This is not quite as favorable as just the two water molecules interacting in this way, even though the relative negative charge on the oxygen is actually stronger in acetone. The reason for that is because because it's, well, one, it's not contributing any positive ends to the hydrogen bonds, but two, whenever you have this hydrogen bond dipole, the bond between hydrogen and oxygen right here, where we've got like relative negative charge up here on this oxygen and relative positive charge down here on this hydrogen, that hydrogen is not only like a relative positive charge that can attract negatively charged things in solution, it's actually just a naked nucleus. It's just a nucleus that's totally exposed to the rest of the solution. So it, even though itself is not carrying a full formal positive charge, actually contributes more positive charge to the intermolecular interaction with that water oxygen than would something like sodium. And so that's why negative charge stuff, why oxygen doesn't just chill in solution negatively charged by itself, because it still can have that charge-charge interaction whenever it has the hydrogen bond, but it's also collapsed its charge. And so it doesn't have, it's like it gets all the good stuff that you have from having a charge interact with water, right? Like the same thing salts get, but it also gets the benefit of not having to have that formal charge, which is energetically unfavorable. And so that's why, for instance, whenever we form a alkoxide, meaning like a deprotonated alcohol, that's why that's not stable at all. Whereas a positive cation in solution like sodium gets to be stable, because what would you react with that sodium? Like there's not a whole bunch of negative ions that carry that are just carrying their negative charge around. They can go dump that negative charge onto sodium to form a covalent bond that then still allows sodium to have that charge interaction with water, if that makes sense. So I just wanted to provide some context for this. And this sort of charge interaction is how you need to be thinking about every organic chemistry interaction on this entire test. This is like, where are the charges? How can we delocalize them more? And where is an opposite charge, and how is that opposite charge going to interact favorably with whatever I have? And if all these interactions are happening what sort of stuff are we going to form at the end? And is that stuff at the end more stable, meaning less charge concentration than the stuff we started with at the beginning? And that's like the essence of determining whether organic chemistry reactions happen or not. Now, obviously, it's more complicated than that. We have all these specific situations we have to memorize. And I'm not saying don't memorize stuff. It's useful to memorize things for this test. Like if you can just pull out very, very quickly that the SN1 happens in polar protic solvents, and you don't have to think all the way through from first principles why, that's usually going to be helpful to you. But if you can think through it from first principles, that's also a useful skill to have whenever you run into a question where you're not completely sure what's going on. So if we do think about like why SN1 does happen in a polar protic solvent versus SN2 can't be in a polar protic solvent, right? It cannot be in a protic solvent. Why is that the case? Can anybody tell me briefly why that's true? Sam, do you know why?
Yeah, I'll wait a little bit and see if
Okay, yeah. I just didn't want to have too much dead air, and I don't mean to put you on the spot. I can also say the answer.
Yeah, I can take a shot at it.
Okay, cool. Yeah. Sorry.
So basically, yeah. So I mean, it just kind of goes back to the idea of stability that Joe was talking about, right? With SN1. So first, I think it's probably useful to define what a polar protic solvent is. So a polar protic solvent, is just like is a solvent that has something that's capable of hydrogen bonding. So something like, I don't know, acetic acid, or maybe not acetic acid, or like just anything like an alcohol or anything that has, you know, the ability to hydrogen bond is going to be defined as a polar protic solvent. And then a polar aprotic solvent is just a solvent that's unable to hydrogen bond. So things like ethers or acetone, things like that doesn't have that opportunity. So the reason why, and this is like going back to like super first principles, or not super, but like it's like a little bit more of the nitty gritty. The reason why SN1 favors polar aprotic solvent is because, or polar protic solvent is because there's two steps to SN1 reactions. The first is the formation of a carbocation. The second step for whatever like the electrophile is going to be for the reaction. The second step is going to be simply that the nucleophile attacks that carbocation and, you know, adds whatever molecule at the site of the carbocation. And the reason why polar protic solvents are favored for this kind of reaction is because the opportunity for hydrogen bonds stabilizes the carbocation site. Because like Joe was talking about, you know, circling again back to the idea of stability, a carbon atom with a positive charge is really unstable in solution. And so anything that is able to kind of provide some kind of support for that carbocation is ultimately going to increase the likelihood that that reaction happens in the first place. And the way that hydrogen bonds are able to stabilize that carbocation is with the negative charge of the electronegative atom that participates in the hydrogen bond. So if you have the carbocation here that has a formal charge, a formal positive charge, the partial negative charges of the hydrogen bond of the protic solvents is able to kind of like, I imagine it as like surrounding the carbocation and kind of like, you know, comforting it, telling it everything's going to be okay. It's, you know, it's not gonna, you know, there's no reason to freak out. And then it's going to be able to stabilize until the nucleophile comes in and, you know, makes the final product the most stable product, where there's going to be no formal charges on the final endpoint of the reaction. On the other hand, the SN2 reaction happens in a single concerted step, where there's like a kind of transition state, like intermediate, that like results. It's not like technically like 5 bonds, but it almost looks like that's what's happening, where the nucleophile attacks the carbon at the same time that whatever is going to leave that carbon is that bond is being broken. And the reason why you want a polar aprotic solvent for this reaction as opposed to a polar protic is that for SN2, the really important thing to know is that you need a really strong nucleophile in order for it to happen, in order for it to occur. And so theoretically, if you were to have a polar protic solvent, that would decrease the nucleophilicity of the nucleophile. Because if you have a polar protic solvent that is able to hydrogen bond, it's going to interfere with the negative charge of the nucleophile. And nucleophilicity, the strength of a nucleophile is pretty directly proportional to, basically how negative the nucleophile is. And if there's anything that gets in the way of that negative charge's like potential to attack the electrophile, then that's going to decrease the probability of the reaction. So since polar aprotic solvents don't have the opportunity to hydrogen bond, it's going to decrease the strength of the nucleophile, which is going to decrease the likelihood of the SN2 reaction and ultimately just, kind of destroy the efficacy of that reaction in the first place, or even to the point that it's not going to happen at all.
Nice. Yeah. Thank you for
that was a super long explanation. Yeah, but
I know you're good. I mean, you just like went in and knocked out both of those two reactions. So I was actually wondering how I was going to incorporate those. So yeah, I appreciate it. So yeah, exactly what Sam just said. The if you're looking at a secondary carbon atom and trying to determine whether SN1 or SN2 is going to occur, the best way to look to determine that is if you can just take a look at the solvent and see what type of solvent you have. Because secondary carbons can undergo SN1 or SN2. But if you see that there's a polar protic solvent, then it can't be SN2 anymore. It has to be SN1. Or if you see that it's a polar aprotic solvent, it definitely can't be SN1 at that point. That's the one more likely to be tested, I would say, because it's more definitive. Polar aprotic solvent cannot possibly be SN1, because if you look at as Sam just discussed, the reaction mechanism there, cannot find the thing I'm looking for now. The reaction mechanism that I drew out this mess. This first step, which is the rate determining step, cannot actually happen if you were in a polar aprotic solvent, because we can't stabilize this carbocation intermediate. And so if the intermediate isn't stabilized, then think about how high the activation energy becomes, right? Or not, I guess technically not the activation energy, but if the intermediate can't be stabilized, then the energy barrier to get through that reaction is just so much higher, because our intermediate is just super unstable. So it would require like a huge amount of energy input just to get to the intermediate, let alone to the product. So that's why you need a polar protic solvent for SN1 to occur. I also didn't want to confuse you all with this like crazy mess of red arrows I drew there with the nucleophile coming to attack. There, I was just emphasizing that the nucleophile can come from any angle in an SN1 reaction. So the reason that and you can see how I drew this as a racemic mixture at the end. The reason that SN1 forms a racemic mixture through the process, and the reason I drew it like this, is because anytime you proceed through an sp2 hybridized state, meaning a carbon atom with just 3 things bound to it, you take on the trigonal planar conformation. The reason for this is because now that you only have 3 things around your central atom, you can have 120-degree bond angles. And so there is actually no geometric benefit to taking on a third dimension, to going into 3D space. You can just stay in 2D space and get these 120-degree bond angles, because you can't actually get a larger average bond angle with 3 things splitting a sphere than you can 3 things splitting a circle, geometrically speaking. Just take my word for it. You don't need to do the experiment there. And so we have this thing sitting in a flat plane. And so the probability of the nucleophile coming in from above is roughly the same as the probability of it coming in from below. There can be steric effects that mess this up. Like if we have a whole bunch of stuff sticking up and nothing sticking down below the plane, then the version where it comes in from below becomes a little bit more favorable. And so in that case, we would get one isomer versus the other one, but it's still going to be split. There's still going to be percentages there. So that's just, just maybe clears up another component of this. Versus in the SN2 reaction, you can see how the nucleophile has to come in first before the leaving group leaves. And so the nucleophile and the leaving group are on opposite poles of the molecule. And that's why you always get that inversion of stereochemistry in the SN2 reaction. We can talk about more specifics of that later whenever we get to the Q&A, if some of you want to go through SN1, SN2. But I think that these are these are really high yield topics, but they're also ones that I'm guessing a lot of you aren't super worried about in comparison to some other stuff. Now, if I'm wrong, please feel free to ask about that, because it's also, if you don't have it down, this is something to definitely get down. It will be tested. Versus like the Gabriel synthesis stuff, not so much like likely to be tested, although it's a good question. Okay, so that's SN1, SN2 reactions. Going back to, I'm trying not to get lost or too lost here. So we were talking about the reason that the solvent matters, the reason that the interactions that molecules form or have with the solvent determines or plays a role in determining the types of products that can form, or the type, or whether a reaction is actually going to take place. It's just an important way of thinking through things whenever you are looking at organic chemistry based problems, because you can't always, sometimes you're going to get in this test and forget a mechanism and freak out. But if you understand the way this stuff works, then you don't have to freak out when you forget a fact, because you can regenerate it from first principles, like I was saying earlier. And this is what I mean by that. We could talk more about that too if some of you have more questions. As I'm doing this right now, I'm feeling the superiority of tutoring versus large group discussions because I'm wanting to assess all of your understanding right now before we move on. But we're just going to move on. Okay, so that is the topic of stability that I wanted to address. We also talked about how to predict whether something is soluble in water or not soluble in water. There is another nucleophilic substitution mechanism that I want to go through here, because it is so relevant to all of biochemistry, as well as much of the organic chemistry that you're going to see on this test. When in doubt on this test, if you're trying to determine whether a reaction occurs or by what mechanism something occurs, just go to this reaction. It's like the most common one. So, and by this, I mean the nucleophilic substitution, where you have some sort of carboxylic acid derivative, or even like an aldehyde or a ketone, interacting with a nucleophile to form a new molecule. You'll frequently see this called transesterification, though, even though it doesn't always have to be transesterification. So when I say carboxylic acid derivative, what I mean is a molecule that's a carbonyl. And so at this point, I've drawn an aldehyde, right? But that has something over here that is question mark. And so the question mark can be like an OH, right? In which case it's an actual carboxylic acid, right? It can also be an OR, in which case it is an ester. It can also be a O, or not an O, but an N and some other stuff, right? In which case it's an amide. It can also be a halogen. Okay, in the case that it's a halogen, we call this an acyl halide. Like, for instance, if we said chlorine was there, then we call it acyl chloride. So this X can be Cl, Br, or I. And so back to when I was referencing fluorine earlier, if you go back to that reference, remember that I said fluorine can't be negatively charged in solution. It's unlikely to be stable with a negative charge on it in solution. It's likely to grab up other stuff. And the reason for that was because fluorine is smaller than the rest of these halogens. And so while the rest of them are able to delocalize that negative charge around their valence shells to some pretty appreciable extent, fluorine is not able to do that because it's just too small. And so that's why hydrofluoric acid is the only of the halogen acids. I can't remember the right way to say that, but is the only of the, like, HCl, HBr, HI. All of those are super strong acids. HF is a weak acid. And the reason comes back to this idea of it just not being stable in solution. And so whenever you write out the reaction, HF plus water yields hydronium plus fluoride, the equilibrium lies very far to the left, simply because that F minus in solution is by far the least stable thing in that entire equation, right? Whereas if we draw HCl plus water yields chloride plus hydronium, that lies really far to the right, because everything on the right side is relatively stable compared to the stuff on the left. We can talk more about acid-base stuff at some other point, but understanding this idea of stability is how you predict all the acid-base interactions. It's also how you predict all the OChem interactions and everything else. Anyway, so looking at the rest of these molecules, I also need to write the anhydrides. This is the one that I kind of forgot to put in here. So in all 5 of these, they all undergo this exact same reaction mechanism, which is, I'm just going to draw one of the acyl halides. This reacting with, I don't know, we'll make an ester here. So the reaction mechanism here is 2 steps It involves this negative charge coming in and attacking this carbonyl group. And the reason we know that that's going to happen is because the negative charge, again, is on an oxygen. So it just doesn't want to be charged like that if you're in water. Like water stabilizes negative charge, but it would be better if it could just react with something. And also there's no resonance there too. So that negative charge is just fully on that oxygen here. And whenever it reacts with that relatively positively charged carbon, right, because the carbon is a good electrophile and the oxygen's carrying electrons, it's like a match made in heaven. The pi bonds on this between the carbon and the oxygen the pi electrons jump up onto the oxygen, because if you think about it, of bonds that could break here in order to let this new carbon oxygen bond form, of the bonds that could break, by far the least strong of those is the pi bond, right? Because those pi electrons just have way less bond association energy than the rest of the bonds. And so here, what we proceed via this sp3 reaction intermediate, where now we've got the negative charge on this oxygen, we have our chloride here, and our nucleophile coming in right here. And so we're going to call this the tetrahedral intermediate, or sometimes you'll see it called the sp3 intermediate. They love to test this, by the way. And then from this point, we need to kick off a leaving group, right? Because again, this oxygen has this unstable negative charge on it. And so to consolidate that negative charge, we can have it jump down here, reform the pi bond. And then if you're trying to determine which bond you need to break, right, because carbon can't have 5 bonds still, then you can look at all of these. You can see, okay, I can kick a methyl group out into solution, right? That would be a carbanion, like very unstable. Carbon having a full negative charge on it is no good. We could also kick this OCH3 back out into solution, and to some extent that might happen, but then we just end up with what we started with, right? And so that's not a significant reaction to write out. Or we can kick this chloride out into solution. And as we've been talking about this whole time, chloride is relatively big. It's also relatively electronegative, and so it's able to delocalize that negative charge in its valence shell and just be like very, very stable in water alone, even though it's charged. And so that is going to be our product of this reaction. We're going to end up with this new ester compound plus our negatively charged chloride. And this over here is just way, way, way more stable than the thing on the left, right? And so we know that our delta G of our overall reaction has to be less than 0, just because this is far more favorable than all of this is. So one thing that's useful to know of all of these carboxylic acid derivative molecules is which ones are most stable versus least stable, right? So if you're looking at all these, trying to determine most versus least stable, I recommend looking at stability of the leaving group, because the leaving group and the nucleophile are the two things that are unhappy, right? And in this whole reaction, like the two least stable things in this whole reaction mechanism I just drew were first most stable is the OCH3. Next most stable is the tetrahedral intermediate, whatever, that's not stable at all, because it's an intermediate. And then the chloride, you can maybe make an argument might be something less stable, but chloride's pretty stable. So we want to think about the stability of the leaving group to determine the reactivity of one of these compounds. So of these, looking at them very briefly, we can see that the only one that when you take the leaving group and just throw a proton on it, the only one that forms a strong acid is going to be the acyl halides, right? So by forming a strong acid, that means that the thing that it would form if you added a proton to it is pretty prone to dissociating, right? Like it definitely wants to dissociate. And so chloride is the only conjugate base, or chloride, bromide, iodide. Those are the only conjugate bases of strong acids that we have as any of the components of any of these molecules. And so those are by far the most reactive, because the leaving groups are just the most stable in solution. So we give that number 1. Second most reactive here is going to be the anhydride, because the leaving group in its case, if you look at the molecule, the leaving group is all of this, right? Like if we have a nucleophile come in, and say nucleophile is here now, just forgive my art, but nucleophile is right there. The leaving group is a carboxylate anion, meaning that it is the conjugate base of a carboxylic acid. While not a strong acid, these do dissociate appreciably in solution because of their ability to delocalize that negative charge from one oxygen onto the other oxygen. So we've taken it and we spread it out. So now rather than having a full -1 charge on any one atom, now we have like a -0.5 charge on both oxygen atoms, if that makes sense. So that's why that's the second most reactive. Third most reactive in this list, and at this point this is probably the most difficult distinction to make here because we don't have any delocalization of any electron density anymore. But so we're going to be looking at these three. And if we think about what is the most cool with having a negative charge on it, nitrogen versus oxygen, the answer here has to be oxygen because it's just more electronegative than nitrogen is. They're in the same row, but oxygen's just one space to the right. So it's just more electronegative. So it's just happier having that negative charge on it. So we can go ahead and rule our amide as our least reactive thing we have. This is the amide, least reactive. We'll come back to that in a second. And then have this battle between the ester and the carboxylic acid. At this point, we have to consider two things that are really, really similar to each other. They're both going to have negative charge on oxygen. So how do we determine which leaving group is more stable versus less stable? In both cases, the leaving group is going to look like this, right? Just O, and then I think I only drew O and then something, right? O and then either hydrogen or O and some more carbons. I'll draw 2 carbons in this case. I'll give it a second carbon there. The idea here to determine which of these is going to be more stable comes down to, again, just like everything else, density of charge on that oxygen. In the case of the OH, the case of the hydroxide, that oxygen has a full negative 1.0 charge on it, right? It's because it's got 1 extra electron. Okay, and that makes it a strong base. We know hydroxide has a pKb of 0 or Kb of 1, right? That makes it a pretty strong base, and so pretty bad leaving group. But if we look at the OR molecule, or the OCH2CH3, as I've written it, you'll see that you've got that full negative 1.0 charge on oxygen, but you also have this electron donating effect from the alkyl group. So chains of carbons are going to have an electron donating effect when in conjunction with an electronegative atom like oxygen, because even though that oxygen has that full on -1 formal charge on it, the oxygen nucleus is still pretty packed with positive charge. And so it's just going to pull electron density from that carbon chain. And so you'll have a little bit of an electron donating effect. So if you want to call the charge on the hydroxide oxygen a -1.0, you can say this is like a -1.1 or something like that. Like it's really, really close, but the OR is just slightly less stable in solution. So in this case, I drew ethoxide. It's just slightly less stable than hydroxide. And so for that reason, the carboxylic acid is more reactive than the ester because it has a slightly better leaving group. Better meaning less bad because they're both bad. But so that's how you order these. The reason this is important is, for instance, if we had drawn a reaction, we could talk about, like, you know, for instance, it could ask you about a reaction where we have a carboxylic acid plus some, we'll just draw the alkoxide like I just drew a second ago, some like OCH3 minus, and they could draw this complex with sodium and say that this is at equilibrium with this thing, right? So if we drew this and asked for the KEQ of this reaction, and you can type this in the chat maybe, I guess, KEQ of this reaction, is it going to be greater than 1, 1, or less than 1? The equilibrium constant of this thing. Greater than 1, less than 1, or 1. I'll give you like 5 seconds if anybody wants to type it in the chat. I don't really care if you do or not, though. I just want to have some sort of participation factor. So if you think about what equilibrium constant is products divided by reactants, right? So if you put concentration of products divided by concentration of reactants into, you know, just a fraction here, then what we're going to find is that because the carboxylic acid has a slightly more stable leaving group, meaning this OH is slightly more stable than this alkoxide, that the equilibrium lies slightly in favor of our product. Sorry, KEQ is going to be, yeah, slightly greater than 1. Thanks, Angela. So anyways, that's just one way of thinking about why the stability of these compounds actually matters for whether the reactions are going to occur, because they could ask you a question like that on the MCAT. That could absolutely be a discrete style question. Okay, so moving on from here, this mechanism, even though I've been talking about carboxylic acid derivatives, is also incredibly relevant for a lot of your alcohol, aldehyde, ketone, those sorts of reactions as well. For instance, if I wanted to draw this as reacting with a ketone, let's say, we could very easily have the exact same sort of reaction occurring, right? We have this reacting with the ketone. there's just not as much that we can do, right? The nucleophile comes in from right here and binds. And so then we do the same thing where we kick our electron density up onto our oxygen. But that's the end of the story. And so we end up with this compound, and you'll probably grab a proton out of water for that oxygen. When we end up with this, though, is it a racemic mixture or not? That's a decent question, I think. That's another type of thing that I could absolutely see the MCAT asking. Do we have a singular product, or do we get a racemic mixture of products? Or they could also ask you something like, we then put light through a polarizer and pass it through the solution and determine the degree of rotation of the light around that, like through that solution, the polarized light. Yeah, I agree, Angela. Thank you again. Yeah, this is gonna end up being racemic. Reason for that is because the reactant here that's being attacked, again, just like in that SN1 reaction, the reason we formed racemic mixture in SN1 was because the nucleophile could come from above or below the plane with relatively equal probability. Same thing here. This is sp2 hybridized molecule, and so the nucleophile can come from above or below the plane with equal probability. One exception to that is enzymatically catalyzed stuff. So whenever you're doing an enzymatically catalyzed reaction, you are likely to end up with a singular product, despite the reaction mechanism looking like this. The reason for that is due to the chirality of enzyme active sites. And this is more biochem stuff. We can talk about this in a different day if we do more of these. The enzyme active sites, enzymes are usually proteins, right? Vast majority of enzymes are proteins. Proteins are generally formed from amino acids, right? If you know your amino acids, which I recommend knowing for this test, then you will know that 19 out of 20 of them are chiral. So if you have all of these chiral bricks building something, chances are that the emergent thing is also chiral itself. And so you have an enzyme active site, which has the job of stabilizing the transition state for a given reaction. The enzyme active site is not going to be able to stabilize the transition state of this reaction going both directions, the thing coming from above the plane and the thing coming from below the plane. That doesn't make any sense. So the enzyme active site is only going to stabilize the transition state for one of the two optical isomers that could result from this reaction. And so that's why when things happen in biological systems, or you see things happen in vivo, it's just a very, very different situation than whenever the reactions proceed in vitro. Just one of the reasons. Obviously, there are a lot more, some of which seems to be magic still, but we'll probably figure it out in the coming years. So anyway, that's just a little bit more on how to predict the way that these reactions happen. Again, this very, very simple, like two-step reaction, not that one, this very simple two-step reaction is, in my opinion, the most important reaction mechanism on the MCAT, and it's not close. Whenever you see reactions occurring and you're not sure what's going on, just go to this. Think about how maybe this is happening, and how that would work. So for instance, I drew this out right before we started. Let's think about what the products of this reaction are likely to be. So if you look at this reaction, you see that we've got this nitrogen in the ring, this carbon thing bound to it. Carbon's drawn out weird, just like they will do it on the MCAT. So does anybody want to take a crack at like what the product is going to be here? I didn't make answer choices, so I know that's going to be kind of difficult, so no pressure. What if I were to tell you that the product of this reaction is going to be, let's say that the product of this reaction is going to look like this. Oops, I can't draw. These are hard to draw. The product of this reaction looks like this. Is that possible? Am I right? Yeah, it's kind of weird, right? So the reason that this seems to maybe not make a ton of sense for you is that what I've just drawn here is actually the leaving group in this reaction, from at least in the way that we've been talking about it. Because if we want to redraw parts of this, so we can redraw the original reactant, the way that I would do this is to redraw it as by like actually drawing out these molecules instead of doing CO2, C2H5, which is kind of weird. You can draw it like this. And so at this point, we have something pretty familiar, right? Because we have this OH that we gave in our reactants, and we have a carbonyl, right? And now we do have an amide here. So obviously, like, this is not going to be an incredibly favorable reaction. We have to push it forward. That's why we have heat in there too. But the negative charge on this oxygen can just come in here, hit this carbonyl carbon, knock the electrons up onto the oxygen here, right? And then we proceed. I hate having to draw all of this garbage, but I'll try to do it quickly. So then we have, here is our central carbon. Here's the oxygen that was originally bound to it. Here is the oxygen that, yeah, this is super messy. Here's the oxygen that was there. And then here is the OH that came in and attacked. Right. So now at this point, we can have a whole bunch of stuff happen, but essentially this negative charge from this nitrogen, or this nitrogen could take on something like a negative charge. And obviously you need to have relatively stable stuff around, like relatively, well, that's why we have the acid there. I don't mean relatively stable stuff, trying to think of too many things at once. But whenever that double bond reforms, this negative charge can just jump down onto that nitrogen, or technically we go pick up a proton from solution. And then since we put so much HCl in there, or a bunch of HCl in there, we would probably protonate it again at the end. But our leaving group here, being the nitrogen ring, is just the result of the exact same reaction, even though it looked weird compared to how we had drawn it out in the simple diagrams before. So just look for this reaction anytime you see sp2 stuff getting hit with or in the presence of a nucleophile, right? Because then what we end up with here is this nitrogen, again, with it gets protonated. I'll just draw it protonated once in this case, plus this crazy carbon thing that has a whole bunch of oxygens on it. Now at this point, we've got that and this one. So I know that's complicated, but this is similar to the types of reactions that they put in MCAT passages. And if you can recognize that we have a relevant mechanism that you're already aware of that will allow you to determine what is going to happen, even though you've never seen something like this before, or something, it could be something even way more complicated too. Then you're already equipped to solve something that should be way above your pay grade from an OChem perspective. This was really, many of you might know that I went to medical school before I started teaching MCAT, which is kind of a stupid order to do things in. But whenever I came back to start teaching MCAT again after med school, I had gotten really good at the biology and biochem stuff, just because that's what you do in med school. But I had gotten really bad at the physics and OChem stuff because I hadn't thought about that in a very long time. But whenever I started teaching it, I started noticing patterns like this, that even though I'd forgotten many of the specifics of the reactions, I could still get 132s on the the chem phys and the biochem sections, not missing any of the OChem questions, not because I had everything memorized, but it felt like it might actually have become a little bit easier because I'd forgotten a lot of the just like straight up memorize this mechanism, memorize 150 different mechanisms for OChem 2 test. I'd forgotten a lot of that, but was still aware of the general principles of nucleophiles like to attack electrophiles, and things need to be stable in solution, because those are also, these things needing to be stable in solution in order to stick around is one of the most important concepts in pharmacology in medical school too. It helps you think about what sort of solvent you're going to need for different drugs, or what sort of vector you're going to need to use to deliver things. So it's just something to be aware of and to get intimately familiar with now, because it's going to make your life way easier moving forward. Let's see.
Oh, yeah. Joe, I have a question. Hi. I was wondering, for the purposes of like the MCAT, are there going to be other nucleophiles that we should kind of keep an eye out for, other than oxygen, or other electrophiles other than like the carbonyl carbon, to kind of just keep in mind, or are those sort of the main ones?
Oh, that's a really good question. Yeah, I didn't mean to represent. You're right. I've been representing oxygen as like the only nucleophile this whole time. No, it's really anything that has electron density that is not super stable on the molecule itself. You could think about it that way. So it could be negatively charged stuff, but it doesn't necessarily have to be. Like, for instance, if we were to do this reaction the opposite direction, this is probably a decent way of thinking about it. If we were to try to do this reaction in the opposite direction, then you would have this lone pair that's on this nitrogen, and it could come in and attack this carbonyl carbon, right? Because the nitrogen lone pair is, even though nitrogen is going to take on a positive charge at that point, the proton leaves relatively easily, and so the positive charge goes away. And the nitrogen lone pair is really prone to attacking stuff as a nucleophile. So that's just, just one example.
Okay.
You can see halogens be nucleophiles a lot of the time. You just need to have some way of pushing the reaction forward, because they're also really good leaving groups. So they're pretty stable. So you're going to have to, I guess, quote, incentivize them a little bit to make the reaction occur.
Okay.
Yeah, the nucleophilic properties change a little bit from solvent to solvent. So Sam hit on this a little bit. Part of the reason that you need an aprotic solvent for an SN2 reaction is because in a protic solvent, first of all, the SN2 reaction requires a really strong nucleophile. The reason for that is because it has to displace the leaving group itself. Like the leaving group in the case of SN2 isn't just leaving. It's just not just packing up and moving out like in the case of SN1. SN1, you can have a relatively weak nucleophile because your substrate, your carbocation, is a carbocation and it's not very stable. In SN2, you need a really strong nucleophile. And so we do it in polar aprotic solvent partly because those really strong nucleophiles, if you put them in water, are just going to deprotonate water like immediately. And so then they're not nucleophiles anymore at that point. Like if you put OH into water, it's just going to grab a proton from water. Or like if you put a negatively charged nitrogen, that's one that you can use as, it's a really good nucleophile for SN2, is like NH2 with a negative charge on this nitrogen. That doesn't work in a polar protic solvent because it'll just grab a proton from the nearest water molecule, because this is a way stronger base than OH minus is, right? So that's
Okay.
Does that answer your question?
Yeah. So then are there any like common protic and aprotic solvents that you'll see on the exam that we could kind of memorize, or is it just sort of common sense? Like, I don't know, not really like a.
Yeah, I think that there is a list of them somewhere in the Kaplan book. If not, we can probably find one.
Okay.
I wrote some.
It's not like a huge.
Yeah, I wrote some of them out
okay.
here as well while Sam was talking. So here are some of the polar protic
awesome.
solvents. Here are some polar aprotic solvents. I couldn't think of a lot of polar aprotic. I can think of a lot of aprotic. It's hard to think of polar aprotic. Well, I get actually now I can, now that I'm not kind of on the spot, but like really anything that just doesn't have hydrogen bond capacity. So like acetone would be a really good example, right? Because it's got this ketone like that, and that's not going to mess up your strong nucleophile too much. It might react with it to some extent, but not like water will. So that's
Gotcha.
just like one example.
Okay.
THF that I wrote right there. THF stands for tetrahydrofuran. And so it's just like oxygen. It's a 5-member ring with an oxygen in it. So tetrahydrofuran. I don't know. that's what the molecule is.
Okay.
And so you can see how
Okay.
it has a dipole across it, right? Like negative charge over here, positive charge over here. And so that's what makes it polar, but also aprotic.
Oh, yeah. Okay. Awesome. Okay. Thank you.
Yeah, no problem.
I also know DMF and DMSO are also popular polar aprotic solvents that the MCAT likes to put on there. Yeah,
nice, exactly. DMSO is like this. These are both CH3s. Yeah, so, and again, same idea, like that. I don't think it's a bad idea to just look up what some of these look like whenever you see them, when you're going through your world questions or AMC questions. Like you're going to see DMSO and THF 100 million times, probably less than that, but you're going to see them a lot. Might as well just kind of don't memorize them. That's a waste of your time, but have an awareness of what they look like. I think that generally is helpful on the MCAT. Like I don't recommend memorizing the structure of every intermediate in the citric acid cycle, but having seen them at some point can be useful. There are also these trends in names of molecules, and this is getting off topic a little bit, so I'll redirect here, but there are also trends in the names of molecules that can help you understand things about the molecule themselves. And I don't mean the IUPAC nomenclature. I mean things like the name isocitrate, for instance. The 8 at the end tells you that it's probably a carboxylate anion. Like most organic molecules that end in 8, And I don't mean like chlorate, that's not organic. I mean like citrate or pyruvate. Those are generally deprotonated carboxylic acids, right? So pyruvate is pyruvate because it's got a deprotonated carboxylic acid on it. You'll also see it called pyruvic acid. That's the same thing, just with a proton. The benzoic acid that I drew earlier right here, if once we take its proton off, it's called benzoate. Things like that. Acetate is deprotonated acetic acid. So isocitrate, probably deprotonated isocitric acid, I would guess. I don't know that, but it's probably right. So things like that. The PYR in pyruvate indicates to you that there are going to be adjacent carbonyl groups, which is kind of weird. You also see that in like pyrophosphate, though, like the PPI that you see knocked off of ATP sometimes. That is two adjacent double bonded oxygens. And in this case, they're adjacent on phosphates, but that's the idea. I just recommend noticing some of that stuff as you move through. Like, don't try to make a table of it. Don't draw it all out. Like, that's a waste of your time. But just have an awareness, be inquisitive, ask questions, use our MCAT AI thing. There's a small plug for that. Even though, I mean, it like actually costs me money whenever you guys use it. I just want you to use it because I think it's useful. So just be genuinely curious as you study this stuff. I think that that's maybe like one of the most underrated or underemphasized really useful tips that I have that I think helped me a lot studying all this basic science, but also in studying medicine. If you're just wondering about stuff while you're sitting around doing nothing, or like in the car working out or whatever, then you just the act of wondering, even if sometimes you wander somewhere that doesn't make any sense, just doing it habitually, I think is one of the best ways to become intimately familiar with and probably even more importantly, comfortable with all of these ideas. Yeah, so I think Angela's question is actually probably like a good segue for us to do some Q&A stuff in this. So does anybody have any questions in particular? I feel like me like just monologuing can be useful, but I think that if I can answer your specific questions, I mean, there's only like 15 of you here or 14 or something like that. So I think if I can answer your questions, then that might be more helpful. And your questions can be very, very broad questions too, if you want. Can't think of like a really good example of that. Like we could talk more about the nucleophilic reactions if you want. We can also, Samir, did you have a question? I saw your hand raised, but
so I really liked the hydrogen bond opportunity sort of rule. I just wanted to know if there were any other sort of like rules in OChem, like unspoken rules in OChem like this. So yeah.
That's a really good question. I would venture to say, I want to say yes. I can't think of them off the top of my head right now. I have a lot of, I wouldn't say I have a lot. I have a few tips kind of like that for things throughout the MCAT. The hydrogen bond opportunity one is one I made up whenever I was studying for the MCAT. This was like a long time ago, but it just works. It's a really good question. I think it's hard to come up with little tips like that so much as I think there's a pretty great border between that type of little hack thing versus just like things to understand or things to know. Like for instance, one idea I keep wanting to come back to is this idea of a detergent, like what detergents do. That's probably more biochemically relevant as well, but that's also just like a content thing. I'm trying to think. Sam, do you have anything like that? Not to put you on the spot again, but
like kind of life hacky like that? Not really.
Yeah, I'm trying to. Yeah, I'm really trying to think of specific little tips like that. I feel like I have them. They're not jumping into my brain right now.
We can go over them later. I mean, on the spot, like, yeah, you can get back to me later. Totally. That's
you're totally good. Okay, I see two questions in here. One wanting to talk about aldyl condensation and enolization. The other mesylates and tosylates. Yeah, so the mesylate and tosylate thing is one that I never got comfortable with whenever I was studying for MCAT. But yeah, we can definitely go over. I read the OChem book like 30 minutes before we started this. Or when I say read the whole book, I don't mean I read every word in the book. I mean that I opened the book at the beginning and I flipped through it. It took 40 minutes maybe, but yeah, the mesylates and tosylates thing I was taking a look at, those are fundamentally just turning the molecule or protecting the carbonyl group. I read that's in a very, I usually don't recommend the just memorize it thing very much, but those I think might be a good example of one where I do. I'm happy to draw it out here in just a second. Aldol condensation, enolization, yeah, we can definitely talk about that. The aldol condensation I think needs to be like not even referred to anymore by people who do OChem, because it's kind of like just multiple reactions in a row from my understanding. But I'll do the mesylate tosylate thing first really quick. I think that might be slightly easier. I want to get an actual picture of it really quick so I don't have to draw it, because I think it's faster for me to find the picture than to draw it. Yeah, already found it. Okay. So let's see, where can I put all of this? I'm just going to paste this in from the book. So let's see here. So the idea is that aldehydes and ketones are not going to withstand being hit with a strong reducing agent like lithium aluminum hydroxide. And so you want to be able to protect these groups before you do something like that. So yeah, so and actually the mesylates and dosylates I'm sorry, these are leaving groups. I don't know what I'm talking about. So the mesylates and tosylates are designed to be able to get the hydroxide off of a molecule. This is alcohol stuff. I was thinking more the like acetal, hemiacetal. It's the thing that comes like right after this in the book. Anyway, so this molecule right here is once you have put a tosylate on like an alcohol. So if you want to, so alcohol and OH is just not a great leaving group, right? We talked about it being a strong base a second ago. Because it's not a good leaving group, if you want to do a reaction where you're displacing it, where you're getting rid of it and putting something else in, so like you can think, for instance, like an SN2 reaction or an SN1 reaction, even with a primary alcohol or a secondary alcohol, where you want to get rid of the OH and put something else on there. Let's say we want to take like propanol and react it with, is that not this one? There we go. Okay, so let's say we do want to take propanol and end up forming this, right? This is going to be difficult to get done. In fact, it might not get done at all. I kind of want to get a stronger nucleophile. Let's put no, I'll just leave it there. So let's say we want this reaction to occur. The only way to get that OH off is to make it a much better leaving group than it is. And so for that, we will react it with either the mesylate or the tosylate thing and turn it into that atom. So we would turn it into essentially this that I have drawn out right here. If you just imagine that the 3 carbons are this R here, and then whenever, we'll just put them there. Okay, so then whenever our nucleophile comes in for this reaction, it's going to come in and want to displace that, that oxygen off of the R group. And so it's just going to come in like nucleophile. Well, I mean, yeah, I guess if we're doing this would be SN2. So our nucleophile has to come in and hit this carbon. We're just going to say that this is carbon right now. Carbon. It hits that carbon, and then this just all leaves, and it's all in one step because it's SN2. Right. So then we just end up with, our products as drawn down there. I don't really want to redraw it. So the reason that we're doing this is because, again, the hydroxide is a terrible leaving group because it's got that full negative charge on its oxygen and that it can't delocalize. Whereas this thing here, I'll finally just draw it. This whole thing is a really, really good leaving group because it's almost just like the conjugate base of sulfuric acid to some extent, right? Which is really stable alone in solution. And so that is the idea. This is the tosylate. The mesylate is just like it. It just doesn't have that big ring on it. It's just got a methyl group instead of the big ring, hence the Me instead of the TO. The TO comes from toluene, which is like the molecule you use to make it. But that's not important. You don't need to know that. So this would be the other one. And so you can see how these just have really good resonance stabilization. So it all comes down to the idea of a leaving group, just wanting to make the alcohol leave. Does that answer your question? Anyway, I don't want to put you on the spot to like talk or type or anything, but okay, so got another one about the aldol condensation business. So I don't know that I've seen aldol condensation come up in a while. Sam, how high yield would you say aldol condensation is? I get people asking about this a lot, and I just don't have a great appreciation for whether it's like super high yield or not.
In my view, it's not very high yield, like at all.
Yeah.
It's definitely good to know.
Right.
Because I feel like it's like one of those things where it's like super low yield, but if you don't have like a good understanding of it and you do have uh a question about it come up, that you're kind of just like, I just have to give up on it.
Yeah.
But yeah,
Yeah, exactly. Okay, cool.
Yeah.
So
I think it's worth going over,
oh yeah,
but not spending too much time on it. Yeah.
right. Yeah, for sure. Okay, so yeah, let's go ahead and do that. So if you have first thing I want to mention is that if you have a long carbon chain with a carboxylic acid at the end, you can label those carbons. The first one obviously is just like carbonyl carbon, whatever. I've called it carbon 0 before just to make it like easy to refer to. The second one is the alpha carbon. Third one would be the beta carbon. Fourth one would be the gamma carbon. Fifth one would be the delta carbon, et cetera, et cetera, et cetera. Right. The alpha carbon, as many of you may be aware, is more acidic than the rest of the carbons. The reason for that is because when the alpha carbon loses its proton, at that point you should form a carbanion, right? Which is why most carbons are not acidic at all. But the alpha carbon can be somewhat acidic just because whenever it does lose its proton, these electrons that we're holding onto it can jump down here to form a double bond between these two carbons, kicking these electrons in this oxygen up onto, or the electrons in the carbonyl bond up onto the oxygen. So what you end up with here is this enol. Well, it's enolate right now because I haven't put a hydrogen on there, but then it would grab a hydrogen out of solution. And so the conversion back and forth between these two is actually, that is what tautomerization is, by the way. Enolization or tautomerization. So that is your enol. And it's also the first step of this reaction, right? So we had like a base of some sort, we'll just say base, comes in and grabs this proton to kick off the reaction. And so now that you have that negatively charged thing, you just react it with another, you can react it with another aldehyde. It can be the same aldehyde or a different one. I'm going to make it just like a smaller one. I'm going to make this a little bit simpler there. That's better. That's just going to make this take less drawing. But if you just react that with another aldehyde, then you have this negative charge, right, that exists on that oxygen, or you can put it on that carbon, like the carbonyl, or sorry, the alpha carbon, right, because there is resonance between those two. So this can be here as well, right? And so this version of the molecule is also a resonance contributor where we have negative charge right there, or where we have where we have negative charge right there on that carbon. And so that version of it is just really super duper unstable. And so whenever, to the extent that exists, that negative charge can come over here and it's a really strong nucleophile. Like carbanions would be stronger than any nucleophile we've mentioned so far, right? Like negatively charged carbon, just no good. And so that negatively charged carbon will come over here and attack another aldehyde, and it can be identical to the aldehyde we started with, right? And so whenever that happens, these electrons will jump up here. And at this point, I'm going to start just labeling some of this stuff because it's going to be really difficult to draw or to emphasize otherwise. So we'll make that original alpha carbon yellow. We'll make the oxygen on the thing getting attacked be green, right? So then this would be yellow here as well, right? And then maybe we can make like blue for this oxygen, something like that. I just want to make it to where you all can actually see what's happening in this reaction. There are some whiteboard videos in your folders that I have on this as well. And one of you told me that the file was like corrupted or something the other day. So if that's the case, just let me know. I can send you the links. But it's going over a passage from the AAC sample exam that's pretty OChem dense. And I just walked through it over the course of like 4 short videos. I think they're like 3 minutes each or something like that. Anyway, so when this reaction occurs, the hardest part is drawing it out from this point, in my opinion, because we have to draw this like carbonyl carbon that gets attacked with its negatively charged oxygen up here on it. Here's the hydrogen over there. And then maybe we'll draw like the methyl group that was on it here. I'll label that as well. So like this bond is going to be this thing. Okay, and then from there we draw the this is the carbon that came in and did the attacking right here, right? And then we have to draw the carbonyl carbon. So that's the carbonyl carbon, and then the oxygen that's on that carbonyl carbon that attacked. And so we can put that in as well. I think the color coordinating this, whenever you're studying it, if you have a tool to be able to do that, is just super useful. It makes it so much easier to think through this. And so then at that point, this negative charge on this oxygen can just grab a proton from solution, right? And so then we end up with basically the exact same molecule, but no more negative charge on our oxygen. So I'll just copy and paste that to not waste all of your time. Right, because this will just grab, we'll put a proton in solution over here. And so now it's got that. So that is it for aldol condensation. It's just a matter of orienting yourself with respect to the molecules that are present, just because that's kind of difficult. I didn't put the green ones in. So green, and this one's green. All right. Does that answer your question on that? Alpha beta unsaturated bond. Let's see. Alpha beta unsaturated. Do you mean, I'm not sure what you're talking about, Samir. You can just unmute and ask me if you want.
Yeah, so I was just wondering if rather than getting like an OH forming over there, could the electrons on the oxygen, like the green oxygen, just like go back down to form a double bond? And then wait, okay. I think I might be messing something up. Okay, never mind, forget it.
Oh, I think I know what you're talking about. To just like this leaves, right? Is that what you're talking? Like in the case that the OH gets kicked off, I think is that what you're referring to?
Kind of, yeah.
Yeah, I think that there is a scenario where I'm trying to remember what happens in that case. Sam, if you can help me out here, the reaction he's referring to, we would end up dehydrating that OH and just forming a double bond right here. So between the alpha carbon and the beta carbon.
Yeah, I think I could be wrong. I think it's because if you have like 2 equivalents of base, it takes another proton off, and then the like electrons from the alpha carbon just go to the like make a double bond between the alpha and beta, and then the OH gets kicked off after taking a hydrogen. Hold on,
Yeah,
I'm gonna look it up. But
no,
yeah,
right.
I think yeah, what you're talking about, Samir, is just like so the first step with like all the colors still on it, that's like the aldol, and then you can go one step further in the aldol condensation to form the alpha beta unsaturated carbonyl compound.
Yeah, it looks like you take it's either E1 or E2. That's what that looks like to me. Like we're just eliminating the OH group.
Yeah.
Yeah. So, but yeah, you form H2O. I think it makes sense to me that we would need a base. I mean, it kind of depends on if you go through E1 or E2, right? Like in order to do, you have to have a base, deprotonate that alpha carbon, I think, to make it happen.
Yeah.
OH.
Yeah, so it's I think it says E1 or E2, but yeah, so it's pretty much the same mechanism as like when you start the aldol condensation. It's just that you just keep that double bond between the alpha beta carbons, and then yeah, you kick off water, so it's a dehydration reaction.
Yeah, I'm just labeling all this stuff again in this
Mhm.
one, just to make it a little clear. But yeah,
Hmm.
so like see my leaving group water, that's the one that's where the green oxygen goes. I'm reading all the chat, by the way. So which product we get depends on whether it's in an acidic or basic solution. You would need a base to start. So I think heat is probably going to be a determinant here. Maybe other groups that are present as well. Usually, I'm trying to think if you would need another equivalent of base or not. I think you would need 2 equivalents of base to do it. And I think that's what you were saying, right?
Hmm.
Okay, yeah. So I think so to answer your question, Aurora, in the chat, I think that you need to be in a basic solution to start no matter what, but it's just how many equivalents of base you have per substrate molecule, I think, to start out with on this.
Hmm. Yeah, like this reaction mechanism is pretty specific. Like you need a base in order for it to start. So if there's any question about aldol condensation, just know that you need a base in order to take the alpha hydrogen off to gain access to the, be able to tautomerize, which then like causes the reaction between the 2 aldehydes and things like that. Yeah.
Right. Yeah, exactly.
Yeah.
Yeah. So, and this is like forming a beta hydroxy ketone. The first one, not the alpha beta unsaturated, but the beta hydroxy ketone, I think get used to seeing that molecule, because I have a feeling it's going to come up with increasing frequency on the MCAT over the next couple of years, simply because of all of the like fad keto diet stuff, and because it's hard. Like, because ketogenesis is not something people normally think that much about. And this is, so beta hydroxybutyrate it's not the same molecule as this, but it is a similar molecule to this. So maybe just something to be aware of that can exist. But yeah, good questions. These are hard. You guys are asking hard questions.
Also, I'm just gonna throw, it's kind of like tangential. It's not like super,
go for it.
like just relevant to this, but when you're thinking about like whether like to add an acid or a base, I mean, you might be aware of this already, but one thing that's just kind of like a rule of thumb is that when you're thinking about acids, or like putting things in acids or bases, or putting acids or bases into a solution to affect a reaction, acids are most often going to strengthen the electrophile, whereas if you add a base, it's going to strengthen the nucleophile. So that's just like because like sometimes it's hard to orient yourself in terms of like why you would need to add an acid or a base. So just to keep as a rule of thumb, if you're adding an acid, you're most likely going to strengthen the nucleophile of something by protonating it. And then if you're adding a base, you're most likely going to strengthen the nucleophilicity of something by taking in a hydrogen, thereby increasing the negative charge of that nucleophile.
Yeah.
Yeah.
You misspoke right there, near the end. You said to put in the last time you said it right the first time. I just wanted to clarify in case it confused anybody. I think the last time you said it, you said to add an acid, you strengthen the nucleophile. I know you meant electrophile. You said.
Oh yeah. Sorry, I said that backwards.
Yeah. I just wanted to make sure that nobody got confused, because I do that.
Okay.
But yeah, so like for instance, if we were to do this reaction that we were talking about, we'll just say like some nucleophile here. If we have this situation happening and we add an acid to this, the acid's going to protonate this thing, which is going to make the electrons in this pi bond way more likely to jump up onto the oxygen than they would have previously, which makes this carbonyl carbon more electrophilic than it would have been otherwise. Whereas if we had added a base, obviously we don't protonate that carbonyl oxygen, but we do have a chance of, if this nucleophile wasn't already deprotonated, like if it wasn't negatively charged, adding the base could make it negatively charged where it wasn't before, and now it's a really strong nucleophile. Just reiterating everything Sam just said. I literally added nothing there. I just wanted to say it again, because it is a really good point. Anyway, so another question that came up a second ago that I almost missed. Bavia asked, could we go over common lab techniques like spectroscopy, or ones that tend to come up most? Yeah. So the things that I think are maybe most important are the lab techniques that involve intermolecular forces. The spectroscopy stuff is relevant. You definitely need to know it, but it's not nearly as hard as it was in your OChem class. If you get a fraction of the competence that you had from your OChem class whenever you went over that stuff, then you're good on the spectroscopy. I can send you some stuff. So if you meant spectroscopy specifically, meaning IR spectroscopy, that's just going to help you look at the functional groups on molecules. So I would know the OH peak and the carbonyl peak, and if you know nothing else, you'll probably get all the questions right. Just knowing those two alone. NMR is relevant too. I would appreciate that is detecting odd number nuclei, so like carbon 13, H1, primarily those two things, due to just the way that that magnetic resonance works. I don't really think that it's necessary to explain all of that. And then to think about like splitting, like the signals on HNMR are going to split whenever you have hydrogens due to hydrogens on adjacent carbons. So every split is caused by a molecularly distinct hydrogen on an adjacent carbon, or not even molecularly distinct, is caused by a hydrogen on an adjacent carbon. That's just like a brief summary of it, but yeah, that's just like a super brief summary of it. I might just make something and send it to you all on that, because I don't know that it merits talking about a ton when we're all together, and might just be better to have like a 2-minute video on it. In terms of other lab techniques, so yeah, Angela just mentioned anion cation chromatography. That's the kind of stuff I'm talking about. So like the separation techniques based on intermolecular forces, that's so over tested in my opinion. All of the chromatographies, be aware of them. Generally speaking, in a chromatography, there are a lot of different types of chromatography, but generally speaking, the idea is that we get some sort of stationary phase and some sort of solvent phase, and everything that you put into the column or into the TLC plate, whatever it is that you have, is going to stick to the stationary phase if it has interactions with it, and it's going to stay in the solvent phase if it has interactions with it. All the different types I could go into. I'm probably not even super familiar with all of them. I just look for hints whenever I run into this kind of stuff in questions. So like, for instance, you mentioned cation, anion chromatography. Cation, anion chromatography, I would say, is you just need to remember the names and which one means what. So anion chromatography means that the column binds anions. Am I correct on that? Somebody please fact check me on that, because I always mix those two up, but I think that's right. So anion chromatography means the column binds to anions, meaning that the first thing that comes off of the column is going to be positively charged, right? Generally speaking, in that case, you would have a solvent that is going to pull that positively charged stuff off and allow the negative charge to stick on. So you could think of using water there. The solvent's not going to be great at pulling the positive charge stuff off if it is not water, like if it's not protic, because the positive charge stuff's not going to be soluble in it. But then you can start adding salt to the solvent as you do this to get the negative charge stuff off as well. So you're like replacing the negative charge interactions with the column. So in the case of anion exchange chromatography, you think, what is the stationary phase? Well, it has to be something that's positively charged, right? In anion chromatography. Cation chromatography is just everything that I just said, just flipped. TLC is usually going to have some sort of polar stationary phase and non-polar solvent. You can have reverse phase chromatography that is just flipped. That is just flipped. So I would say, as long as you can be aware of what your stationary phase is and just think about what things are going to stick to that, then you should be good on chromatography, I would think. Is there, Sam, would you add anything to that, to chromatography?
Not really. I mean, there's a couple other kinds of chromatography that
Yeah,
you just kind of have to be aware of, like high performance liquid chromatography and then gas chromatography.
Right.
There's nothing like super special about either of those, aside from the fact that, let me see, I'm just like looking at my like content thing here.
Yeah.
Yeah, just the HPLC just gives you higher resolving power, and then gas
Right.
chromatography is you vaporize the liquid, so it's like you separate based on with gas.
Yeah. Like
And then
more-
also I think just keeping like the overall just very big picture like purpose of chromatography is really simple. It's just to separate two molecules.
Yeah.
So as long as you have that very like simple basic like understanding of why you want to do chromatography in the first place, I think that could actually really help you in like guiding your understanding of questions related to chromatography and just the ideas themselves.
Yeah. Fundamentally speaking, all of the separation techniques, which means like the vast majority of the techniques in OChem, are going to be just looking at what is different between two molecules and how can we exploit that to keep one and get rid of the other. That is the idea with all of the separation stuff. And so like I like that as just a first principle for thinking about something you've never seen before, because it happens to me all the time. Students bring me passages and I'm like, I've never seen or never heard of this before in my entire life. And I always have a brief moment of feeling like an imposter. And then I remember, no, I've done this a million times. And I like, even though I don't know what it is, if I just distinguish, okay, what are the key facts about this? Or what are the key principles that I know speak to MCAT relevant topics, then you can work your way through it. I think that that's maybe the most, just like in general across the MCAT, that's one of the most important tips I can give you, even though it's very non-specific. So usefulness, I don't know, but like once you get there, you'll know it. is the best way to describe that. So just thinking like, okay, what is different between these two molecules and how are we going to exploit that? That gets harder the more similar the molecules are. Like for instance, in enantiomers, you can't use most separation techniques on enantiomers. The only way to get those separated from each other is to start crystallizing them, right? Because they're going, by crystallizing, you're building molecules on top of other molecules of the same type. And so like enantiomers of one another are not going to come out with the same crystallization pattern. So you can pull one out, or to distinguish them based on rotation of plane polarized light, obviously, or to put them in some sort of chiral chromatography or some sort of chiral separation technique to where you're only binding one-handed molecule, not the other, because they have the same melting point, same boiling point, same reactivity with achiral stuff. It's only chirality and rotation of plane polarized light that is going to help you distinguish them. But then as molecules get less and less similar, like for instance, you get out to diastereomers, those are more easily separable because even though they have many of the same things, like same molecular mass, same functional groups, all of that, there are certain polarities in the molecule that exist in one diastereomer and not the other. Like for instance, cis-trans isomers is just a good example of that. So that gives you more tools. And then as you get further out, like constitutional isomers are super easy to separate because they have different functional groups. So like ether versus ethanol, same molecular formula, but ether is way lower boiling point, or sorry, way lower boiling point than ethanol is. And so you can just boil it and get it all out of the ethanol, for example. So that's just how I would recommend thinking about like intermolecular forces and separating molecules. That kind of takes this kind of almost full circle for this entire discussion. It's like start with intermolecular stuff, understand the electrostatic interactions between these things, like positive likes negative and vice versa. Positive doesn't like other positive. Positive and negative both hate nonpolar. Nonpolar likes itself, right? And then just work from there to think about what is and is not stable. Because generally you're going to trend towards stability. It's just like thermodynamics. But yeah, let's see. Any other questions?
Joe, sorry, I had a quick question following up
Yeah,
for the
go ahead.
chromatography. Sorry, this is on my phone, so I can't figure out how to like use the raise your hand
Oh, yeah, no, you're good.
Like-
No worries.
signal on it. But I was wondering so for like, for example, with anion exchange chromatography, when
Mhm.
the column binds the anions and then the cations get eluted, then like if that's correct.
Yeah, nice.
Okay, then I think there was a practice problem or on one of the practices or something where it was like, okay, after you elute it, then what solution or like what compound would you add next to like get the thing that was stuck on
Mhm.
the column eluted from the column?
Yeah, nice.
And for some reason, I always found that really confusing. Like, is it like if it's anions, for example, attached to the column, then would you add more anions to like replace the bonds, or would you add cations to like for the anions to bind to and then leave?
Theoretically, yeah, good question. Theoretically, you would add anions to replace the ones that are there already. That's what I would say.
Okay.
However, in practice, good luck adding anions without cations. You're going to shock yourself to death. Yeah, like just because
Yeah.
if you had an exclusively anionic solution and you get close to it, it's going to electrocute. Like there's going to be charge come out of that out of the
Yeah.
solution.
Okay.
So that's why it says add salt, just because practically speaking, you can't have anions alone in solution.
Gotcha. Okay. So
Yeah.
then if you added like table salt, even if there's cations there, you would still have the anions to like replace the previous ones.
Right.
that how it
Yeah,
would work?
exactly.
Okay.
Yeah. The anions would come off and replace the previous ones, because there'd be some sort of, and you can think about this from the perspective of equilibrium, right? Like there'd be some sort of equilibrium constant for the interaction between the molecule of interest and the column, and another equilibrium constant for the reaction or the interaction between the new anion you just added and the column. And so they're both going to just proceed toward equilibrium. And so because there's none of the anion you just added already bound to the column, then that equilibrium has a long way to go before that system has a long way to go before it reaches equilibrium, and it's going to displace the other one in the process, if that makes sense. So you just have to add a bunch of salt.
Yeah. Okay. Yeah. So it's not like you're getting rid of all of the attached
Right.
compound. It's just you're probably getting like that's just how you're going to get rid of like some of it.
Correct. Yeah, and I mean you get rid of like principally all of it, and not like enough of it, but there are many I would say most interactions you have in biology or chemistry or any of the stuff that we're learning about, you're never going to have completion of anything. Like
Right.
every chemical and physical system exists in relationship to an equilibrium, and those equilibria are never zero and they're never infinity. And so for that reason, like no reaction ever goes to completion. It goes to equilibrium. Every reaction does.
Okay.
Yeah.
Okay. Thank you.
Oh yeah, no problem. That's generally just like an important principle too. Like when people ask me what the most important chapters are in this stuff, and you've all probably heard me say this at some point because I'm a broken record, but when people ask me what I think the most important stuff is on the MCAT, I think it's equilibrium, like bar nothing. Just because if you understand equilibria, like how reaction quotient relates to KEQ, then you can figure everything else out from there. Provided obviously you know some vocab and know the parts that you're dealing with, but everything is governed by that, because that's just like first and second law of thermodynamics combined is literally all that is. Like delta G, you can calculate the delta G based on the relationship between reaction quotient and equilibrium constant. And if you can calculate the delta G, you know whether something is disposed to happening or not happening. And I just recommend thinking about everything from that perspective. Like once you get into medicine, keep doing that because it's super relevant. Any other questions from anyone? I've got like 15 minutes left. All right, cool. So one thing that I'm trying to decide, I do want to do more of these. I think that they can be useful for people, and it's easy. It's obviously like I could talk to a bunch of people at once doing it this way versus one person at a time. And especially right now where I know a lot of you are cramming for September test dates. I do want to continue doing it. I'm trying to think about ways to make it better though. I think having Sam here is super useful. I won't put you on the spot. I didn't mean to put you on the spot the times that I did, Sam. So sorry about that.
Hey, Sean.
Obviously having more people is better, not for any reason other than I'm trying to run a company. And so if some of you bring in people who aren't already customers with us, then that's kind of nice. But no obligation to that. I'm just trying to add value in a way that is not going to cost people a whole bunch of additional dollars to do that. And so if we can make this be something that is as good as it can be, then I think that will make it worth doing more. I would love feedback from any of you, either now, you can do it now, or message me privately if you want, or send Julianne a message. I really don't care. Just give me some feedback on things that you liked or things that and more important, things you didn't like from this, so that I can make sure that the next time we do it, it's better. Because I've got some ideas on how to improve it, but I don't know where the primary pain points are. And I'm not going to leverage like 5 of my hours trying to create some polls or something like that if that's not something that's going to be super effective. Also, the stuff that we taught today, I'd never taught that like that before. And so, because a lot of you wanted to do OChem, but moving forward, I'm going to try to have, I have kind of ways of going about teaching specific topics that I've done a million times. And so moving forward, like for instance, if we had done endocrine or light and optics or any of that other stuff that was on the list, I had stuff for all of that, but most of you picked OChem. So I wanted to do what you wanted to do. I think that it could maybe be useful to do some passages at some point, but I didn't want to bring in a passage that some of you hadn't done and just totally ruin it for you. So that's why I did not do that. But any feedback right now that anybody's willing to give? No pressure. Okay, well, and you can also just message me. Common pitfalls, certain subjects. Thanks, Samir. I really appreciate it. Yeah, common pitfalls on certain subjects is a really good idea, Angela. Cool. Yeah, I appreciate both of you saying those things. Both nice and feedback is good. So yeah, common pitfalls on OChem specifically, I would think, and I kind of alluded to this a lot, but I would say that maybe the most common pitfall is freaking out because you don't remember the exact reaction that you're looking at having happened somewhere in your notes or somewhere in class or something like that. Because OChem tends to be, at least from the university's perspective, very memorization heavy course. It's not like that on the MCAT. There are some things you have to memorize, obviously, like you need to memorize what THF is, that is polar aprotic solvent. You need to memorize the properties of nucleophiles, but generally speaking, systematic thinking is a lot more effective on everything on the MCAT, even psych soc, than just straight up memorizing. There's some of both, but common pitfalls. So most common pitfall for OChem is just like panicking and not being confident enough to see, oh, this thing I've never seen before is actually just abiding by the exact same principles as these other things I have seen a lot. So look for simplicity amongst the complexity. And if you're confident in doing that, then you're much more likely to see it happen. That's why many of you have also probably heard me say that you need to be confident on the border between confidence and arrogance whenever you go in to take the test. And don't tell anybody about that. You won't have friends if you do, but know that you're the smartest person alive whenever you go in to take the test, and that you do know this and you have put the work in. Obviously that's easier said than done. But one way that helps it be easier to do is studying a lot, because then you'll have you'll have the appreciation that you have put in the time. But yeah, so I'd say that's like a pretty common pitfall. Poor understanding of equilibrium and of acids and bases specifically, I think is a huge pitfall on OChem. One of these meetings soon, if we do more of these, probably like the second or third one, maybe fourth at the latest, that we'll do is going to be covering some acid and base stuff. Even though I know many of you probably already know this pretty well already, I just think I have a good way of going through it. I think, and there are a few of you who I've already gone through it with, but I think that could be useful. And the reason that it's good for OChem is that if you understand what makes something a strong versus a weak acid, or a stronger acid versus a weaker acid, then you also understand what makes a good versus a bad leaving group, and what makes a good versus a bad nucleophile, because those are the same ideas. So I would recommend that as well. Yeah, I wish, unless I like the comment, I wish we could like bottle up confidence, but if we could do that, then we wouldn't be an MCAT company. So I don't know. We'd just be like a confidence company, make my life way easier. Now I'm thinking about other, like, I don't have really other pitfalls necessarily that come off the top of my head. Sam, do you have anything? I said earlier that we would ask you like how you had studied for all of this. So I'm curious to hear that out, but some of the other people are.
Yeah, so as far as like pitfalls, I think really the only thing that I would say is like, and you've touched on this a couple times throughout this meeting, but one thing that I guess would separate people who are really comfortable with doing like OChem and just like the Chem Phys section in general versus people who aren't really comfortable with it is really just like how much they understand versus how much they just memorize the material.
Yeah.
And for exactly the reason that you just said. So it's just honestly just reiterating your point in just different words. yeah, because if you're able to kind of pick apart like big picture ideas from the questions that you might not be familiar with, like the specific concepts, more often than not, you'll be able to, you know, find the right answer, even if you don't know all of the content.
Mhm.
Yeah. I mean,
yeah.
like huh?
Oh, I just said, oh yeah, for sure. I was just agreeing as vehemently.
Yeah.
Yeah.
So yeah, because I mean, you know, I definitely am not like the most comfortable with all this material, but there's just a few, you know, big picture ideas that I'm very familiar with, that I can kind of use and kind of recognize in the question stems. That's, you know, it makes it a lot easier for me to navigate those questions. So yeah, that's just like general advice that I would say. As far as like how I studied for the MCAT in terms of like Chem Phys, it honestly really just goes back to that same principle of understanding like big picture patterns, and learning to apply that. As far as like specific material, I think the Kaplan books are really just like the best way to like understand content, like raw content. And then for like big picture things, it was a lot better for me to use like interactive like material. Like I was one of those guys that went on the MCAT subreddit pretty often. But also I would like watch YouTube videos and stuff. And
I
yeah.
was saying no. Don't, like
Um,
I tell everybody like stay off of this MCAT subreddit. Like you guys gave us money.
yeah, that
We have people
right.
who are really good at this. So just ask us. That's
yeah.
Anyway.
Yeah. I would recommend that. That was only yeah. I would recommend staying off the subreddit as much as possible, just for your own mental health. But yeah. Yeah, but and then I would use like Anki for, or like flashcards for like just hammering material like that I just needed to memorize. Yeah. So
What
nothing
about
too special.
what about this? What about days where you didn't feel like studying or making yourself actually get through all of this? Because I know it sounds trite, but it is also the hardest thing for most people on this.
Sorry, could you say that again?
I think
maybe my internet was cutting
no,
out.
I think
Or
it was mine.
okay.
That is very sad. I've been having some internet issues lately. I thought it was totally fixed too. So testing it right now. But what I was asking is, what about on days where you didn't feel like studying or where you were having a hard time like forcing yourself to get everything done? What are some strategies you have on that? Because, and I'm not like, if you have no strategies or you've never had a hard time studying, then props to you. But I was just curious because I'm trying to get everybody's opinions on this, because if that's something that we could facilitate for people or make it easier for people, just like to force yourself to do the hard work somehow, then that would be amazing. Because I think that that's the hardest thing for most people, myself included.
Yeah, I think I mean, there's definitely a lot of different reasons for why like you could just not feel up to studying. And so I feel like it just kind of depends on it. Like I would say like an important step is first finding out why you don't like feel motivated to study. Is it because you have a lot of other things going on, or is it because you feel like, you know, you don't have like, you don't think it's like worth it? Like, oh, I'm just not going anywhere with studying. Like it's not going to be a good use of my time. For me, a lot of the times that I felt that I wasn't up to studying, the reason was just because I was like feeling like I can't get any more into my brain right now. And so yeah, it wasn't anything to do with like outside life circumstances. It was more just like, oh my gosh, like I feel like I can't really do, you know, more right now. And in those situations I mean, at some point, I don't know if I still have it, but I like scheduled out what I would do for every single day of before, you know, my studying. And if you look at my schedule, I had so many just like what I called like rest days that were not planned. And so, yeah. And so
Yeah.
I think that was honestly pretty important for me to just like maintain some level of motivation, especially as I was getting to like the harder parts of like taking full length exams and things like that, was really just having like built-in days where I could not think about the MCAT at all.
Yeah.
Or like very like lightly think about it. And then and then just kind of go from there. I think retrospectively, I think a lot of like m- uh, hmm. retrospectively, the best way to prevent burnout is, and just like it, like in my uh situation, or like similar situation to me, would be to try to plan it out as much as possible beforehand.
Mhm.
Um, and plan to build up your tolerance, if that makes any
That's a good
sense.
tip. Yeah.
Yeah. So because I think I was trying to do that, like I was trying to juggle like studying for uh the test while I was also like trying to figure out how I was going to keep myself motivated to study for the test. Um, if that makes any sense.
Yeah.
And so I was like trying to, I was trying to figure out how I could take care of myself while also figuring out how to study for it. So I think if you kind of are able to set aside some time to like really meaningfully think about how to, um, for lack of a better word, take care of yourself before you get into the nitty gritty, that's going to be your best bet um, for like keeping motivation.
Yeah.
Um,
Totally agree with that. Yeah, that's really smart. To take care of yourself is a good tip, generally speaking. Like work out
yeah.
daily. Try to work out daily. I'm a massive hypocrite too. Like I'm not going to work out today because I don't feel like I have time to do that today. Same yesterday, but you guys should. So, yeah, those are all really good tips. I think also to the burnout point, planning things out ahead of time, like both your days and your weeks out ahead of time before you start studying, is a good idea. Don't spend more than 10 minutes planning. Like that's a waste of time. Because some people like to spend all day making their study plan because that makes them, it's a procrastination tactic. So don't do that. That's not what I mean. But what I do mean is know the amount that you're trying to get done in a day before you get started so that when you get that amount done, you can be done. Because that is what burnout is. I've probably spoken to a few of you about this as well, but there's some recent evidence that suggests burnout is more of a PTSD fear related phenomenon than it is a I'm tired of studying and a fatigue related phenomenon. So if you tell yourself ahead of time what you have to get done and then you go do that and then you quit for the day, then you're done after that, then you'll develop a sense of trust with yourself that you probably don't have very much of right now because you don't trust yourself to be a reasonable master. You don't judge yourself to be a reasonable boss that's going to tell you I do X, Y, and Z, but not everything else, or do A, B, and C, but not D, E, F. Or if you tell yourself you're going to have to do D, E, F today, and then you also do whatever G, H, I don't know the letters, then you're going to lose a sense of trust with yourself and you're going to be more prone to burnout. It doesn't mean you're for sure going to be burnt out. And also limiting the amount or planning out your day ahead of time doesn't mean that it's going to fix all of your burnout in a week. It's going to take a little bit of time, but that seems to be one of the most actually evidence-based effective approaches to either mitigating or treating burnout. Anyway, I'm going to have to run. I have another meeting in like 30 seconds. But I will tell Julianne to send out a message. If any of you have any feedback for me in addition to what we've said here, please feel free to shoot me a text. I think you all have my phone number. If you don't, email me and get my phone number because you should have it. Shoot me a text, send me an email if that's easier for you, whatever you prefer. And just let me know how this went, what you might want to see different in the future, and any criticism. Like criticism is way more useful than compliments. I appreciate the compliments too, but criticism is super useful for me on this. So please criticize away. And let me know if any of you have any questions, obviously. All right, I'm heading out. Have a good one.
Thank you.
See you, Joe.
Yeah, no problem. See you later.